Okay, so hello everybody, good morning and welcome to lecture 13 of our course. So if I take a quick look at our course plan, it might appear that we are running a little bit behind schedule, but that's okay, we'll catch up quickly. And also another thing is that along the way I've been discussing on the topic. So it's, I've already discussed some of the material that we will need later on in the course. Okay. All right. So let's see. All right. So are there any questions from the last time or this time? Will any questions at all? No. Okay. All right. So in the last class, and again, please stop and let me know if at any point my audio is unclear. Is it clear at this time?
Yes, sir.
Can somebody tell? Yeah. Okay. Great. Okay. So in the last class, I had started talking about time reversal symmetry, right? And what we saw is that we expect the microscopic laws of physics to be invariant under time reversal. So in particular, let's say Newton's second law. And we, okay, and so the time reversal as long as the force doesn't have a component which depends linearly on the time. For example, if you add a friction component, so then this component will be proportional to the velocity, and this introduces dissipation into the system. So whenever you introduce dissipation into a system, you lose time reversal symmetry because the system no longer has the information needed to reverse the evolution, right? That is lost in or other forms of energy exchanged with the environment, right? Then we looked at the Schrodinger equation, and the my updates are happening slowly. So we looked at the Schrodinger equation, and we asked what should be the effect of time reversal on this equation. And what we saw is that if you work with time reversal as an ordinary unitary operator, then under the effect of this operation, the Schrodinger equation is not invariant at a time reversal. But again, that goes against our expectations because if you have a Hamiltonian that is time invariant, time reversal invariant, then if you take a state and you evolve it in the positive direction or the negative time direction, there should be no physical difference, right? And so we looked at the example of a plane wave. All right. Okay. So, am I audible? Can somebody please confirm?
Yes, sir.
So time reversal should have something to do with complex conjugation, and also that it cannot be an ordinary unitary operator, right? So today we will look at this in a more rigorous manner. All right. So let's say that you have a state psi at some time t naught, and then so we have this. This is the time reversal operator. Now we're using this symbol theta, capital theta, for the time reversal operator. And then you evolve this time reverse state by some amount delta t, right? So this evolution, what is the time evolution operator? Time evolution operator is, well, again, psi t is equal to I h bar d by dt psi t. And if your Hamiltonian is time independent, then psi t is equal to minus I h bar t h t by h bar by psi 0. So this is the unitary operator for time evolution, right? Because it's taking the state at some time, initial time, and giving you the state at a later time. So if you evolve the state forwards in time, what do you get? You get exponent minus I h bar h hat t by h bar acting on theta, acting on psi. Okay. Now we can do one more thing. So this is one state. Okay. We can also do something else, which is that we start with the state psi naught. Then we evolve it backwards in time by minus delta t. And so that gives me exponent I h hat delta t by h bar. I put delta t. Right. So what is this? This is psi of minus delta t. And then I can apply the time reversal operator to this state. So the claim is, so I can write this. So the claim is that if I act on the state with the time reversal operator and then evolve it forwards in time, okay, I should get the same state as if I evolve backwards in time. That means u minus delta t first, and then act on the time reversal operator. So, let's say that your system is described by some trajectory. Okay. Of course, in quantum mechanics, we don't, particles don't move on specific trajectories, but for the sake of argument, we just assume that that is the case. And you start at some time t is equal to 0, right? So this is t is equal to delta t, t minus delta t. Okay. And now your particle, let's say here, has some momentum t at some time t is equal to 0, right? So now if you take the time reversal of this momentum, well, what do you get? You get just the minus p, right? And then we evolve this forwards in time, right? So we evolve it forwards in time, we get something like this. Let's say minus p with u delta t acting on it, right? The other possibility is that you start with p and you evolve backwards in time, right? And then you act on it, then you take the time reversal. Let me try to use a different color. This is the, so this is the time reversed part of the backwards evolved momentum. Okay, well, I won't go into it more than this. This is a little bit confusing, but this should be true. Okay. This should be true if your Hamiltonian is time reversal invariant, right? And why is that? Because if your Hamiltonian is time reversal invariant, then evolving forwards using u delta t should give you the same result as evolving backwards, right? Okay, now, so what we do now is we take this operator u delta t and we expand it, Taylor expand it. So u delta t is this operator. And if I Taylor expand this exponential, I just get minus I bar t by h hat t by h bar. And similarly, u of minus delta t will be identity plus I h bar t by. Okay. And I substitute these two expressions in this equation. When I substitute these expressions in there, what will happen is I will get terms which are proportional to the identity, they will cancel out. Okay, so we can work it out explicitly. It's not very difficult. Is equal to theta psi 0. So on both sides, you will get one factor of theta multiplied by psi 0, then minus I by h bar, h hat t, and then theta psi 0 equal to theta psi 0 plus I. Now here we have to be careful, and I will keep the order of all the terms exactly the same. Right. So now these two terms cancel out, they're the same. I can get rid of h bar, that's the same. I can get rid of t, that's a real parameter, right? Real parameters are not going to cause us any issues. And so finally, we are left with this expression. So I'll bring both terms over to one side, and I can write as theta I h hat plus I h hat theta psi naught is equal to 0. Now, the first instinct would be to think that, well, in this expression, this I, factor of I square root of -1 is just a number, right? But it's just a complex number, so I should be able to cancel it. And so if I cancel it, what do I get? I get that theta h plus h theta acting on psi naught is equal to 0. Okay. But there is a problem with this, because if you assume that this is true, so let's say that psi naught is an eigenstate of h. So if psi naught is an eigenstate of h, then we have h psi naught is equal to E psi naught, where E is the eigenvalue, right? And so this expression will become h hat acting on theta psi naught is equal to, so this goes over here, minus E theta psi. And this, okay, so it's all the same color, and that doesn't help in distinguishing. Okay. So what this expression would tell us is that if psi naught is an eigenstate of h with eigenvalue E, then the time reversal of this state, which is theta acting on psi naught, is also an eigenstate of h with eigenvalue minus E, right? Because this is theta acting on psi naught, theta acting on psi naught. So this expression is telling me that the time reversal of psi is an eigenstate of h. And what is the eigenvalue? It's minus E. In other words, this would imply that for every time reversal invariant Hamiltonian, right? Because remember that we have started out with the assumption that our Hamiltonian is invariant under time reversal. Every eigenstate of h comes in a pair with eigenvalues E and minus E, right? So if this is true, then in any system wherever h is a time reversal invariant Hamiltonian, now we can look at a simple time reversal invariant Hamiltonian. Let's say p square by 2m plus 1/2 k x hat squared, right? What is this? This is the harmonic oscillator. Now, this is invariant under time reversal, right? Because you have square of x and square of p. So under time reversal, theta under time reversal, h is just h. Right? And what are the eigenstates of this Hamiltonian? The eigenstates are have the eigenvalues h bar omega times n plus 1/2 n, right? These are the eigenstates labeled by some number n, which is the number operator. And I hope you remember all this from the first semester. H bar omega is the frequency, right? And n belongs to the natural numbers, 1, 2, 3, so on. But now here, we can see that this is not true, right? Because for a given eigenstate n, there is only one eigenvalue, which is the positive, this energy, h bar omega, right? Right? So there is no time reversed state here, right? So obviously, there is something wrong there. We have made an error somewhere because we are ending up with a contradiction, right? We started with the assumption that our Hamiltonian is time invariant. If our Hamiltonian is time invariant, it should, under time reversal, it should satisfy this condition. But this condition is not true for a sample, an example time reversal invariant Hamiltonian, which is the harmonic oscillator, or even the free particle. Okay, so what is the error that we have made? The error we have made can be traced back to this step where we canceled out the factor of I. So now we know that time reversal should have something to do with complex conjugation. Right? So what this means is that if I take the time reversal of some state which is multiplied by some number, any number c, and there's some state psi. Ordinarily, for any normal operator, this would just be equal to c. You can just take the operator through, right? But for time reversal, I have to put a complex conjugate, right? So in other words, time reversal does not commute with C numbers, C meaning complex. Right. So this is the really new and weird aspect about time reversal, because from everything that you have learned so far, what you know is that when you have some operator, it can be, right, they can be Hermitian or unitary or any other kind of operator. But all operators, at least in the finite dimensional case, you can represent any operator by a matrix, right? Where these are the matrix elements of this operator in some eigenbasis. So if you think about the action of this operator on any state, right, and you put a complex number here, well, since this is just a matrix multiplying a vector, this complex number is not going to make any difference whether you put it in front or in back, right? Where left or right of the operator, right? Because this is just a matrix. So, you know, what you're doing is something like this: A M n, you have some complex number, and then phi n, right? So you can just take the complex number and put it over here. It's not going to change anything. Right? Because these are also numbers, this is also a number. But time reversal is something very strange in that you cannot do this. If you apply time reversal, you have to take the complex conjugate to bring any complex number out. So time reversal, this operator, is what is known as an anti-unitary operator. Okay, so this is something that is different from what you have encountered so far. So as an example, if time reversal acts on some linear combination of states like this, what will be the result? You will get alpha star, then time reversal acting on psi, beta star, time reversal acting on. So you get a complex conjugate over here. And finally, what we learn is that time reversal can be written as the product of a regular unitary operator multiplied by the complex conjugation operator. That means this K is a complex conjugation operator. Okay. So that means if you take, and what is U? U is some ordinary unitary operator. So if we take this, make this assumption that this is true, then let's go back to our previous setup and look at it again. Now we don't cancel out these i's, right? Why? Because I have theta I. So if I have theta I is equal to minus I theta, right? By the rules of a unitary operator. And so this expression becomes minus I theta h hat plus I h hat theta psi naught is equal to 0. Now you can cancel the i's because all of the i's are on one side. And you get that the commutator of theta with h acting on psi naught is equal to 0. And this is good. We are happy to get this. Why? Because this tells us, remember, what do we, when an operator commutes with the Hamiltonian, what can we say about that operator? Remember, anybody?
Symmetry.
All right, so that operator is a symmetry of the system, right? So here, this operator is a symmetry of this Hamiltonian. And that is what we expect because we started out with the assumption that this Hamiltonian is time reversal invariant, right? So time reversal must be a symmetry of my Hamiltonian. Okay. Now there is a lot more that one can talk about with time reversal and with symmetries and so on. This anti-unitary operators, etc. But again, that would take us too far ahead, of course, and we don't have that much time in the semester, unfortunately. So instead, I will mention one very important result without any proof, which is called which is called Kramer's degeneracy theorem. Right now, if you look back here, when we made the mistake of assuming that theta can commute with complex numbers, what we found is that every eigenstate of H comes in a pair, one with positive eigenvalue, one with negative eigenvalue. So whenever you have a system where the same state has more than one eigenvalue, right? Then we say that that is a degenerate eigenstate. So what is Kramer's degeneracy? Kramer's degeneracy is a statement that if you have a particle or system with half integer spin, that means J is equal to 1/2, 3/2, and so on, right? Then the statement, then for any time reversal, if there is a Hamiltonian, which has time reversal symmetry, invariant Hamiltonian, right, which acts on such states, any time reversal invariant Hamiltonian acting on such states right, has degenerate eigenstates, which is the statement that for every eigenstate with energy plus E, I also have an eigenstate. So one second. So this is, I'll call this psi plus. This is E psi plus, and this is psi minus minus. So for every eigenstate with energy plus E, there's another eigenstate psi minus which has energy minus E, right? And so this happens only in systems which have half integer spin, and such systems are actually quite common in nature. So as an example, you can think of any atom with an odd number of electrons in the valence shell. Sodium, right? If I'm not mistaken, this is the atomic structure of sodium. So this has one electron in the outermost shell, right? All the other electrons are paired up. So this will show the Kramer's degeneracy. So when you look at the spectral lines of sodium, you will see a splitting of those lines, right? And that splitting is due to this, has to do with this time reversal invariance. Okay, I think I'll stop here for today. Questions? Probably no questions. Okay, well, I will give you some homework problems. I will send them to you later today. Okay, they will mostly be back of the book problems from Sakurai. Okay, so our next, from tomorrow, I'm going to start talking about angular momentum. Okay, so that has been a long time coming. And we will review what we learned about angular momentum in the first semester, and then we'll go on to more useful topics involve addition of angular and yeah. Okay. All right then. I will see you all tomorrow unless you have any questions. Okay.